Okay, let's get this show on the road. Hello, everyone. Hope you're well. Welcome to another installment of the very popular Math 212 series. Last time we found our heroes in a very precarious position, and we are going to find a way to do, well, whatever, I don't know. Anyway, I am excited for today's lecture. It is, I think it's going to be a very fun lecture. Hopefully by the end of it, you can tell me if it was good for you too. But we're going to see. We're going to talk about power series, more power. And let's actually just do that on. So today's the 24th of June, and we're going to talk about power series as well as their convergence. And yeah, like I said, I think it's going to be very excited about it. Let's jump into it. So some people were saying yesterday they thought of the power series as just, what is that, a series on steroids? Well, let me tell you specifically what it is. It actually has a very specific definition. Okay, so a power series, and normally you can emphasize where it's centered. So we can say a power series centered at x naught, and x naught is just some real number. So I can say, oh, there's a power series centered at 4, or there's a power series centered at 7, or there's a power series centered at 0, or whatever. But a power series centered at x naught is a series of this particular form, right? And the Cn are just constants that come from some sequence. So there's a sequence that's controlling what the constants are for each n. And x is a real variable. So x is like a variable here. I want you to appreciate, though, that x is a variable, but compared to, as far from the series perspective, it's actually constant, right? So the series sees the variable as n. The series itself is not going to affect x, but from our perspective, x is actually a variable. And x naught, like I said, is some particular real number that we're centered about. Now, before we start to understand that, let's actually write out what such a series would look like, and then maybe you can start to see why it's called a power series and why it might actually be useful. So if I were to start writing out this series, what would it actually start to look like? Well, for n equals 0, for n equals 0, I plug in n equals 0, I would just get C0 plus, so when n equals 0, plug in n equals 0, I get C0 plus, plug in n equals 1, I would get C1 times x minus x naught to the 1. Plug in n equals 2, I would get C2 x minus x naught squared. Plug in C3, plug in n equals 3, I get C3 x minus x naught cubed plus dot dot dot. And this keeps going. So here is where I plug in n equals 0, I get that. Plugging in n equals 1, I get that. Plugging in n equals 2, I get that. Plugging in n equals 3, I get that. And then the series just adds them all up. Right? So now, if you look at, let's say we're centered about 0, right? So we're centered about 0, so our x naught equals 0, and I'm plugging it in. What would that look like? Well, it looks like, well, C0 plus C1x plus C2x squared plus C3x cubed plus C4x to the 4th plus dot dot dot. And that's what a power series is. And there is no real simple terms to express it other than that. There is a way that you can express it, but not as a definition. You should know the definition. This is what a power series is. It's a series that looks like that form. It's a very specific definition, and that's basically it. However, at this point, you can probably start seeing why this guy might be useful. And you can probably start thinking about something else that this series might remind you of. What does this remind you of when I write out a series like that? Is there anything it reminds you of? It reminds you of a geometric? Well, it shouldn't. So a geometric would be something that looks like this. a plus ar plus ar squared plus ar cubed plus da da da. The coefficient is always the same. The coefficient is always a. So this is not geometric because the coefficients are changing. I have a C0, a C1, a C2, a C3, etc. So it's not geometric. Make sure that by the time the test comes around, we know the definitions of what all the series are. So it's not geometric. What else does it remind you of? Remember, your C's here are just constants. What do you know that would look like something like that? Like a constant plus a constant times x plus a constant times x squared plus a constant times x cubed. Anything comes to mind? No? You guys are thinking way too complicated. Okay, before you were in this class, if an algebra student saw something like that, what would the algebra student think? It's also not alternating. I'm not sure. Are you guys just throwing out phrases now? The signs don't change. So it can't be an alternating series. No, it's not exponential either. You guys need to look up the definitions of all these functions in series. And they're not just buzzwords that you just throw out. Exponential means the base is a constant and the power is a variable. Something like that is exponential. And you wouldn't have an infinite sum. This guy, you'll notice, hopefully, looks like a polynomial. One of the first kinds of functions you've ever seen in your life. Right? It's a polynomial, right? You have a constant plus a constant times x plus a constant times x squared. It reminds you of a polynomial. Now it's weird, but of infinite degree, if there were such a thing, right? Because notice that the powers of it just keep getting higher, right? For a bigger n, the powers just keep going up. But as from looking at this little thing, the little pieces, the little piece of the series that I wrote down, it should remind you of a polynomial. That's what it should remind you of. It wasn't any of those other things you guys pointed out, which means you really need to look up your definitions and know specifically what these things are. It's not a geometric series, it's not an alternating series, and there are no exponentials. So none of those words should have come to mind. That being said, it looks like a polynomial. So the power series are essentially, they are, for lack of a better phrase, infinite polynomials. If you want to know what a power series is specifically, it's a series that looks like this. However, they are a great model for polynomials of infinite degree. And another thing that you guys would notice about polynomials is that they're actually very algebraically nice, right? Think about what you've been doing with polynomials. Think about calculus with polynomials. If you have to integrate or differentiate a polynomial, super easy. This is not the case with any other random function. Polynomials are very nice. They're continuous everywhere. You can differentiate them anytime. They're not undefined at any spots. They're really nice functions in general. So that's one thing that you'd want to notice about polynomial, right? Now, the kind of a polynomial is really just a sum of power functions. A generic phrase for a power function is something that looks like x to the n, where n is a constant. That's called a power function. And so a power series is just a series of power functions. Hence, they call it a power series, right? So polynomials, really nice. And a power series is essentially like an infinite polynomial, a polynomial of infinite possibilities. Possibilities are endless, okay? And that's why it's called a power series, right? Because a power polynomial is just a finite series of power functions. If you go with an infinite series of power functions, you call it a power series. So now, the series above look like they might be useful. Hopefully you notice that. But let's actually get into when these series will converge. So let's say, okay, I have a series like this. Now we want to be concerned with, what does it even mean to be an infinite polynomial? Does that even make sense to even say? Like, are you even saying words right now? Yes, it does make sense in some sense. And then we can talk specifically about when these series would actually be mathematical objects that we can actually manipulate and do calculations with. And this comes down to us talking about their convergence. And the following comes as a theorem, which we're not going to justify, but I'm going to state it. It's actually very important that you know this theorem, but you don't need to know how to prove it or anything. There are three possibilities when it comes to power series for whether or not they will converge to something meaningful, right? So, and it turns out the answer, just like how these guys look like infinite polynomials, it stands to reason they're going to be nicer than general series. In fact, a power series will always converge. There is no such thing as a divergence for a power series. It's always going to converge. The question is, where is it going to converge? For what x values will it converge? It's always going to converge. It just depends on where. Now, one possibility, and this is the smallest possibility, it will only converge for x equals x naught, right? So look at this thing that I wrote out here. This is an infinite sum. One way to make sure it converges is plugging in x equals x naught. If you do that, you'll notice that every term here is going to go to 0 because I have x minus x naught as all the factors. And that's going to converge to the number c naught. So it's possible for it to converge at one point. And that's honestly the worst case scenario. Another possibility is it will converge for all x values, meaning I wrote this guy out here. So suppose I wrote out this guy here, and I let anyone choose whatever x they want to plug in. You can plug in x equals 1, plug in x equals 1,000,000, plug in x equals 1,000,000,000,000, plug in x equals 14. But whatever you plug in, this infinite sum, if you do one of the convergence tests on it that we had before, it's going to converge to something meaningful. It's possible to converge no matter what you plug in x for. A third possibility is that it only converges for some x's. In fact, it will only converge on a certain interval of x's. Namely, there's going to be a bunch of x's around the x naught for which it converges. And this is where the idea that it's centered at x naught comes from. There will be some interval that opens around x naught where x naught is going to be dead in the center. And you will find that it's going to converge for all x values within that interval that is centered at x naught, and it will diverge for everyone outside of that interval. Now, potentially, at the endpoints at that interval, it may or may not converge. That's something that you would have to check extra using one of our convergence tests, but it will converge within that interval sometimes. Now, whenever it converges for some other points, maybe for all x values or for x values in some interval, the convergence is absolute, which is very important. So whenever this guy does converge to something that's not completely useless, it turns out the convergence is absolute, which we know is pretty good. That means we can actually do math with it. We can manipulate it. We can differentiate it. We can integrate it. We can do all sorts of things with it. Now, the number r that describes the interval in which it converges, that's called the radius of convergence, right? So those are the possibilities. Now, you'll notice that if I were to flesh this out, the x minus x naught in absolute value is less than r. If I were to expand that by using what I know, or what we know since algebra class absolute values mean, it expands into something like this, which is the interval that we can talk about. And if you can write it in interval notation, and based on whether or not it converges at one or both of the endpoints, these are all the possible scenarios for a radius, an interval that it will converge on. So it'll converge like over here or over here. It converges on the left endpoint, but not the right. It converges on the right endpoint, but not the left. It converges at both endpoints, or it can converge at neither endpoints, but converges in the middle. So these are all the scenarios that you can have in case 3. Now, if we generalize the r to be equal to 0 or infinity, which neither of these guys will actually make any sense if you actually plug it in here, but if we pretend that it could make sense, if I plug in r equals 0, then there is going to be no point where this is going to work. So it's actually going to collapse into the situation in case 1. And if you plug in r equals infinity, then these intervals will become infinitely long, and it will it will converge on the entire real line. Now I'll show some illustrations of this in a little bit. But before that, let me actually give you the definition. This leads us to the definition of the interval of convergence. So it's simply the interval that's described by this, where one or both endpoints might not be included. It's also possible for the radius of convergence to be infinity, in which case it has no endpoints, and it converges on the entire real line. And I said that in red, what I just said here. If your r equals 0, there is no interval, and that brings us into case 1, where it's only going to converge for that one specific point. If r equals infinity, then that gives you the entire real line. If you plug in infinity into these intervals here, you get from minus infinity all the way up to positive infinity, and that gives you the entire real line. Otherwise, there's going to be some interval of finite length. The length of that interval is going to be twice the length of r, and that's going to be where we can converge absolutely. Now, at the endpoints, we may or may not converge. This is something that we have to check separately. So to illustrate this, here's what we mean. So in case 1, it's possible for that power series to converge on, well, only at a point called x0. So boom, one possibility is our power series only converges here. And that means it converges when I plug in x equals x0. In fact, it converges to whatever the value of c0 is. And in this case, we would say r equals 0. The radius of the interval where it converges is 0. It does not converge on an interval. I can also say something like the interval of convergence is undefined. It doesn't really have an interval of convergence. Although you could probably think of it as, well, it converges literally for a set with one thing in it. Another possibility, case 2, is here's my real line. Here is the point x0, but it doesn't even matter because literally everywhere on this real line, it's going to converge for the entire real line. It's possible to converge for every possible x value. In this case, I would say r is equal to infinity, and my interval of convergence is just the entire real line, the interval from minus infinity to infinity. That's case 2. Case 3 is often the most interesting case. So here I have the real line. Here I have x0. Then there is an interval of finite length where x0 is in the center, and it converges everywhere inside that interval, but it diverges everywhere outside of that interval. So r will have the length here. So this is r, which is equal to k, which is some finite number. And notice your x0 is dead in the center. So it can extend all the way up to x0 plus r, and it can extend all the way down to x0 minus r. So I can center things at x0, and it unfolds on either side of x0 by an equal amount called r. So here I can say r equals k, some finite real number. And my interval of convergence is going to be, well, it goes from x0 minus r all the way up to x0 plus r, where the endpoints may or may not be concluded. Endpoints may not work. Okay, so this is a power series. It's just a way to write down an infinite polynomial. It turns out they always make sense. They always converge. Worst case scenario is they will converge at one point. However, they can also converge on the entire real line, meaning no matter what x value I plug in, it's going to make sense. Or they can converge in some window centered at x naught, but they will diverge if I plug in any x value that's outside of that. And the endpoints may or may not be concluded. However, whenever it converges on an interval, inside that interval, the convergence is going to be absolute convergence, right? So that's going to be very nice. That's a very useful theorem. And knowing the radius of convergence and the interval of convergence is also very important. So we'll get to that. Now, here's a question. How would you find the ROC and IOC for a power series? Well, you'd use the ratio test. And in Calc 2, it's always the ratio test. You always use the ratio test. Now, you might wonder, why is the ratio test useful? Did I say that here? Now, you might wonder, why would I use the ratio test? Well, recall the ratio test. Hopefully you remember the ratio test. Ratio test says we converge if L, which is equal to an plus 1 over an, is less than 1 in absolute values. Now what you'll notice is that ultimately this comes down to when you simplify, some blah is less than 1 in absolute values, which ultimately means that I can unfold that blah. So an interval naturally arises. So using the ratio test is very natural for an interval to automatically pop up. This is also true for the root test, but the root test is a little bit harder to get to work in general. The ratio test is going to be nicer. When it comes to a power series, always use the ratio test to determine the radius of convergence and the interval of convergence. So let's actually do some examples, because at this point, I would expect that most people are confused. So here are some power series. And I'm going to find the radius of convergence and the interval of convergence of those power series. And I'm also going to answer this question pretty soon. Let's move that to the side though. We'll come back to that guy. Okay, so for now, we're going to just look at these power series. We're going to find the radius of convergence and the interval of convergence of these power series. Okay, so I'm going to take one for the team. I'm going to do the hardest example. And maybe you guys can help chime in and help me with the other one. Okay, so look at this series here. This happens to be a power series. Notice I can write it out. This is going to look like, if I plug in n equals 0, well, 1 plus x squared plus x cubed plus x to the 4th plus going on forever. Notice if I wanted to write this out like very pedantically, this would look like 1 times x minus 0 to the 0 plus 1 times x minus 0 to the 1 plus 1 times x minus 0 squared plus dot dot dot. So this is basically a power series where my Cn is equal to 1 for all n. And x naught is equal to 0. So if I wanted to create a power series where the coefficients are always 1 and my x naught is centered at 0, this would be the series that you would create. Now notice here, for example, you can ask the question here, and I'm elaborating a little here. Does this always converge? Meaning, does this infinite polynomial always make sense? Well, how do you know? Well, let's check. I can plug in x equals 0. And the series basically gives me 1. Makes sense. I could plug in x equals a half. And what would happen to this series? Well, the series would give me 1 plus a half plus a fourth plus an eighth plus, and that also makes sense. We know that equals 2. Makes sense. Right? This is from the dichotomy paradox, one of the first examples that we looked at. We saw that a half plus a quarter plus an eighth plus etc. equals 1. You add 1 to it, it gets 2. So if I plug in x equals a half, it makes sense. If I plug in x equals 0, it makes sense. What if I plug in something else? What if I plug in x equals 1? Then the series is going to give me 1 plus 1 plus 1 plus 1 plus, hey, that's infinity. Makes no sense. So clearly, for this power series, I'm not allowed to plug in any x value I want. However, there are some x values that I can plug in that will work. I found 2 of them right here. 0 is going to work and 1/2 will work, but 1 does not work. So now the question is, what other x values can I plug into this series to make sure that it works? And when someone asks a question like that, what they're really asking is, what is the radius of convergence and the interval of convergence on this series? For what set of x values on the number line will this series actually make sense? I know 1 doesn't work, and I know 0.5 works, but what else would work? I don't know. To figure that out, we are going to find the radius and interval of convergence. So to know where this will work, to know where the series, the power series makes sense, to know where the power series makes sense requires finding the ROC and IOC, right? So you might be wondering, why would I need to do this? Well, for one, for sure, I'm going to ask you about it in a test, and for sure, it's going to show up on your final at some point. But for another reason, it's actually going to be important. We want to know, when did this thing that I just wrote down, when does it actually make mathematical sense? When is it actually a number that I can use in a math equation? And everyone's going to say, oh yeah, that makes sense, right? That's very important. What do you mean, how do I know that x naught is equal to 0? Because it's right here. Right? Like, you don't have x minus anything, right? The base is always going to be x minus x naught. So if the base is only x, then x is automatically x minus 0, right? I also wrote that out here, right? So if your x naught is 0, that's what it's going to look like. If your x naught is anything else, it's going to look like this. So our x naught is and it's funny, it's actually not. It's x naught. Right. Not as in a word that means nothing. I don't know why they call it. You can call it x sub 0, but most people call it x naught. Right. So here is a power series. How do I know it's a power series? Well, look at it. Look at what it expands to look like. It looks like an infinite polynomial, so it's definitely a power series. And then using this, I can write it as a power series. And so that's how it actually looks like. This is a power series where the coefficients are always 1 and my x naught is equal to 0. So in my power series definition, if I plug in 0 here, and then I plug in 1s here, so let the sequence be the sequence 1 all the time, it would result in me getting this series. Now let's figure out for sure where this series is going to work. So to find ROC and IOC, what are we going to do? I love how it's like ratio test? Question mark, ratio test? Always use the ratio test, right? I don't even, why are you guys like so timid? Like always use the ratio test, right? So if you're a Calc 2 student, someone asks you to find a radius of convergence and interval of convergence, it's always the ratio test. Not in general, but in Calc 2, it's always the ratio test. So use the, well, that the is a word. Use the ratio test. Always in Calc 2. So that's what I'm going to do. So the ratio test says L is going to be equal to an plus 1 over an. And that's going to be the limit. So I think I left off the limit in a rush last time. This is going to be a limit. Okay, so what would that actually look like here? Well, my an is just the general term of the series, which here it looks like x to the n. So I'm going to put that in. So this is just the limit of x to the n plus 1 over x to the n. This, of course, leaves you with the limit of x. Now, remember, the limit is in terms of n approaches infinity. So what is the limit as n approaches infinity? Well, there are no n's, so it's just x. So now what will you do is you set the absolute value of x less than 1 for convergence, because that is what the ratio test tells us. So this means r equals 1. The radius of convergence is 1. We'll see another way to determine this later, because determining it at this step, it happens to confuse a lot of students. We'll see another way to determine this later.
And if you were to move on to the next step, which is the interval of convergence, think about in order to set it the interval of convergence, you see the radius 1. It's supposed to be like negative r less than x less than positive r. Then after that, once you determine that, then you're going to have to plug in whether or not it's the negative 1 and the positive 1, which are like, the endpoints, whether or not if they converge or diverge. If they converge, then it's less than or equal to. If they diverge, then it's just less than. So what I got was like, like negative 1 less than x less than 1.
Right. So now if your x is less than 1, this means that we have minus x minus 1 is less than x less than 1. Now what you're going to do is you're going to check the endpoints. So you're going to go x equals negative 1, and you're going to plug into the series. So if I go to my original series and I plug in x equals negative 1, the series is going to look like minus 1 to the n. Now you're going to say whether or not that converges. Does it converge?
No.
No, why not?
Because if you plug in like infinity, it would diverge, And another thing, same thing
That's
goes with
not why. And plugging infinity doesn't make sense. How do I know that this diverges?
It's alternating, so it's going to alternate between negative 1 and 1.
Not clear enough, no. Alternating doesn't automatically mean diverges. Right? You can have something that's alternating that converges. So telling me that it's alternating and that's why it diverges isn't how you would know. Remember your training, grasshoppers. You have a series. You want to know if it converges or diverges. What is the process that you go through? see a random series, actually, does it converge or diverge? What do you do first? Right, you do the test for divergence. And you'll immediately get that this diverges. Right, if I take the limit of -1 to the n, I do not get 0. That's how I know. I mean, there are multiple ways to know, but that's the easiest way to know. It diverges. Not because I can plug in infinity, not because it's alternating. It diverges because I ran the test for divergence. So it diverges at -1. If I plug in x equals 1, I would get the series 1 to the n. And again, which diverges? Again, by the divergence test. The limit of 1 is not 0. The limit of 1 gives me 1. So this means I can now determine what is the interval of convergence. The interval of convergence is going to be this interval, except I'm not allowed to use either of the endpoints. So the interval of convergence is just going to be the interval from -1 to 1.
Well,
Now,
that's
of
what I
course,
got.
good, but you need to get it for the right reasons, because then with a problem that's harder, you won't figure it out. So here, we know that this is centered at 0, and it goes up to +1, it goes down to -1, and it works in between this, but it doesn't work otherwise. Now, if you wanted to figure out what is the radius of that, the radius is just going to be half of that length, right? R. So here, the whole length is 2, which means the radius is just half of that. So that's just 1. So I can also conclude from this that the radius of convergence is 1. And the interval of convergence is the interval -1 to 1.
Professor, why can't we use like -1 less than x less than 1 for the interval of convergence?
You can. It means exactly the same thing.
Is that for the same thing? So
Yeah,
if I were to-
that's like me writing a half and then someone saying, why couldn't we write 0.5? You could. It's exactly the same thing. So that's your radius of convergence and your interval of convergence, right? This is interval notation. It's just a shorthand for writing an inequality, remember? So that would be the radius of convergence and the interval of convergence of this particular series. Okay. So I see a series. I know it's a power series. I know it's a power series because there's like an x there as well as an n. That's a shortcut for how you'd recognize it in this class. But the important part is it looks like an infinite polynomial. Then if I wanted to know where does this actually work? Where does this power series make sense? Where does it make sense for me to use this to derive some math equation or use it to figure out some problem? Then you would have to find the radius of convergence or the interval of convergence. And to do that, you always use the ratio test. Applying the ratio test allows you to take a limit, and you're going to find some interval here that you get when you set it less than 1. Now, immediately you should be able to figure out what the radius of convergence is from that, because notice that this is in the form x minus x naught less than a number, and we've defined the radius of convergence to be the number such that x minus x naught is less than that number. But it actually confuses students a lot of times. So I would say, even if you don't get it this way, just hold off, because once you figure out the interval of convergence, the radius of convergence is just going to be half the length of that interval. And of course, once you find the interval of convergence, you don't know ahead of time whether the endpoints are going to work. So what you would do is you would plug in the endpoints. You'd plug in those specific values into the series, and then you would run a series convergence test, which we covered in the last lecture, to figure out whether it converges or diverges, which means you need to go through that process that I explained before. First, run the test for divergence. Does it look like a geometric series or an alternating series or a P series? Does it look like something that I can integrate easily? Does it look like a rational function so I can use a comparison test? Does it have factorials in it so I should use the ratio test? Like these are all things that you'd have to be able to do while doing another problem, right? So you should be very good at figuring out whether a series converges by the time you get to this problem, because you're going to be doing it while figuring out something else. Okay, so yeah, that's the first one. Now, I had a very long-winded explanation here. Let's actually get through the other ones. So here is another example. And again, this is also a power series. How do I know? Well, look at what it expands as. This expands to, if I plug in n equals 1, I would get x minus 4 over 2. If I plug in n equals 2, I get x minus 4 squared over 4. If I plug in n equals 3, I get x minus 4 cubed over 12 plus dot, dot, dot. This looks like a polynomial. In fact, I can write it out in a different way if I really want to make it look like the guy. So it looks like 1/2 x minus 4 plus 1/4 x minus 4 squared plus 1/12 x minus 4 cubed plus dot, dot, dot. I could in fact include a 0 here. So this basically tells me that my C1, my C0 is 0. Here my C1 is 1/2. Here my C2 is 1/4, and so on. So this looks like a series where, so this is a power series. Where Cn is equal to 1 over 2n for n greater than 0, and Cn equals 0 for n equals 0, and my x naught is actually 4 in this scenario, right? So it is a power series. If you expand it, it looks like a polynomial of infinite degree. It is centered at 4, however. So that is a power series. Now let's actually find the radius of convergence and interval of convergence of that guy. So what do? We employ the ratio test. Always the ratio test. This leads us to figuring out this guy. So I'm going to look at the series, plug in n equals 1 everywhere, then I'm going to divide by when I plug in just n. So this is x minus 4 raised to the n plus 1 divided by 2n plus 1, multiply by the reciprocal, and that's my limit. Now, of course, at this point, hopefully we know how to use the ratio test very well. So we can group these guys. Now I start to simplify. This cancels, well, all of that. And so now I end up with this particular limit, the limit 2n over 2n plus 2 times x minus 4. All right, what does that limit approach? No. No. Remember, this is the limit as n approaches infinity. So n is the limit. The limit does not affect the x. Right, x minus 4, right? Because this part here, this limit goes off to 1 just by ratio of leading coefficients. So I'm left over with just the absolute value of x minus 4. It's important that you keep the absolute values. Okay, now what we do is we set this less than 1 for convergence. So you're going to force this to be less than 1. this automatically tells you that the radius of convergence is 1, but let's actually continue. So this means that I have -1 less than x minus 4 less than 1. This means if I add 4 to all sides, x is less between 3 and 5. And now I would check the endpoints. So when I plug in x equals 3, what would the series become? So I go into the original series, plug in 3 here. Notice that when I plug in 3, 3 minus 4 is going to be -1. So this guy looks like -1 to the n over 2 to the n. Converge or diverge? Converge or diverge, quickly. Well, not too quickly. That's right, it converges. If that's not something that you can see right away, it's a problem. This is an alternating series. The limit goes to 0 and it's decreasing. Now, if I plug in x equals 4, yes, don't forget, and especially don't forget on test day. You need to have,
Actually, x equals 5.
like this, you need to have this table burned into your brain. You need to have done
Professor?
so many of these problems so that
Professor,
this is like second nature to you. You know when you see a series, your mind immediately gravitates towards the correct thing. And this is x equals 5.
That's what I said, x equals 5.
Now, if I go and I plug in x equals 5, what's going to happen? So if I look up here, plug in 5 in this position, I would have 5 minus 4, which is just 1. 1 to the n is obviously just 1. So I get this. Converge or diverge? You should already see the answer. In fact, this is something that, again, 2 to 3 seconds, you should see the answer here. So this diverges. Hopefully you saw that. Why does it diverge? Limit equals 0 is irrelevant. Because here the limit equals 0 and it converged. So limit equals 0, irrelevant. Right, it's a divergent P series. It has P equals 1. More specifically, it's a specific kind of P series. It's harmonic. Again, something that should be burned into your brain. You should spot, oh, that's harmonic. 1 over n, right? You can factor out the 2. So it's harmonic, so it diverges, which means the left endpoint works. It converged by the alternating series test. The right endpoint did not work. So this tells me that the interval of convergence is 3, including the 3, all the way up to 5, not including the 5. Now, by the way, this also means that the radius of convergence is 1. And how would I know it's 1? Well, you can do your little thing where you can draw the interval here. If the center is 4 and you go all the way down to 3 and all the way up to 5, what is the distance between that? From the 4 to the 5 has a distance of 1.
Professor,
Yes.
why did the 5 diverge? Why isn't
Because
it
I plugged
converge?
in 5. When I plug in 5, I get a harmonic series. Harmonic series diverges.
And how come, when you got x equals 3, how come it converges?
Because it's an alternating series, and I did the alternating series test.
Okay, so it's supposed to be like, parentheses, like, -1. So what, and it's supposed to be the same thing here, parentheses -1 to the n power over 2n, and if you plug in 5, I mean, like.
No, if I plug in 5, I don't get -1. 5 minus 4 is +1. If I plug in x equals 5 here, I get +1. So it's not alternating at 5. So that is the ROC and IOC there. Where's the next example? Here's another one. We're going to run out of space. This. Jeez, I'm spoiling the surprise. We're going to talk about that after. Let's do this one. Okay. So again, here's a power series. You should be able to recognize the power series. Plugging in n equals 0, I get 1. Plugging in n equals 1, I get x. Plugging in n equals 2, I get x squared over 2 factorial. Plugging in n equals 3, I get x cubed over 3 factorial. Plugging in n equals 4, I get x fourth over 4 factorial. Dot, dot, dot. So here, my x naught is 0, and my Cn is given by 1 over n factorial. It's a power series. Okay, now where does this power series work? Where does it converge? I would, for ROC and IOC, apply a ratio test. So I'm going to compute the limit of x to the n plus 1 over n plus 1 factorial times the reciprocal. I'm going to compute that limit. So this is n factorial over n plus 1 factorial. And this is x to the n plus 1 over x to the n. And this whole thing cancels that whole thing. What is n factorial over n plus 1 factorial? Right, 1 over n plus 1. So this whole thing is going to cancel the factorial part of that. We'll have that. Now, if I take the limit as n approaches infinity, what happens here? Right, 0 times x, which is another way of writing 0. And here's the cool thing about 0. This is less than 1 always. In particular, it's less than 1 for any x. It doesn't matter what you put in for x here, you're going to multiply by 0. In other words,
What I'm assuming, it would probably, your radius of convergence would probably be infinity, and the interval of convergence would probably be negative infinity less than x less than infinity.
correct, because any x value would work. So your interval extends forever in both directions, which means your radius is infinite right off the bat. right? So this is an example of a series, a power series that will converge for all x values. It does not matter what you plug in for x. You can plug in 1,000,000 for x. This series is going to converge. It will be an infinite sum that adds up to something meaningful. In the second example, this does not always add up to something meaningful. This series does not always have meaning. It only has meaning if you're plugging in x values between 3 and 5, not including 5, but you're allowed to include the 3. This series, the first example, the series of x to the n, that guy converged on the open interval -1 to 1. As long as you're plugging in x values in that interval, the series is going to add up to something that makes sense. Outside of that interval, it will not make sense. All right. Here's something, though, that I want you guys to consider, and don't take too long. It probably shouldn't take you too long, but it's going to be a nice segue into the next section. What does that series converge to? So the first example I looked at, we know it converges between when x is between -1 and 1. What does it converge to? Take a while, think about it, but don't take too long. Any guesses? And the hint here, this is like a throwback to something that was mentioned earlier. So someone mentioned something, and I said, no, it can't be that thing because the coefficients were all different and blah, blah, blah. However, if you look at this example, the coefficients were all the same. So I have a 1, and the coefficient here is a 1, and the coefficient here is a 1, and the coefficient here is a 1. So this series should remind you of something. And I'm not talking about a polynomial. I'm talking about something else. What does it remind you of? Anyone? Maybe I'll write out the hint. So let's write this out. If n equals 0, I get 1 plus x. You know what? Let me multiply that by an x again. That gives me the next one. What if I multiply that by an x again? That gave me the next one. Well, if I multiply by x again, I get that. Not exponential. Like what? There's a real fascination with exponentials. It's not exponential. But listen to how I just described how I was finding the terms of this series. Start with a 1, then I multiply by an x to get a next term. Then I multiply by an x again to get the next term. Then I multiply by an x again. Geometric. It reminds us of a geometric. Right. So earlier someone said a power series reminds them of a geometric series. And in general, this is not true. But for this power series, that is true. This reminds me of a geometric series. In fact, the x kind of functions like an r. And what is the a? Well, the a is the first term, which is 1. So this is actually geometric. Now, as long as your r Now, since we know that x is this, it gives us that r is this, so it converges. Absolutely. Absolutely. To, well, we should have this memorized by now, a over 1 minus r. This means this series, x to the n, I can think of it as 1 over 1 minus x. As long as my x is between minus 1 and 1, that series describes the function 1 over 1 minus x. And I don't know, some of you might not see it yet, but that is beautiful and actually really useful if you start to think about it. Look at the function 1 over 1 minus x. When you think of that, what do you think of? Well, some of you might think of the graph, and that's between, of course, of your x equals 1, it's undefined, and the graph looks like this. Right? Or it might actually look the other way. Because you think of the graph 1 over x, and you multiply it by a minus 1, right? Because this guy here, you can think of this as minus 1 over x minus 1. So you take the 1 over x graph, you shift it to the right by 1, and then you flip it upside down. So it actually goes the other way. Oh no, I did draw it correctly. Okay. What's this? Now what you'll notice is that if I cut things off here at minus 1, and not include that, then this entire part of the function here can be described by a series. In fact, we can even do even better, not just any series, but it can be described by a power series. That deserves at least one explanation. Okay, so we just show that this converges for x values between minus 1 and 1 strictly. What would it converge to? Well, if I view it as a geometric series, that is what it converges to. But what is that? That's just a function of x. Which function of x? This function of x. And between minus 1 and 1, meaning I'm only looking at this part of the function, but if I'm on that part of the function, in that window, this series is that function. In other words, it is possible for me to think of this function as an infinite polynomial. So there are going to be contexts, of course, in which this function is really annoying to use, but a polynomial is not going to be annoying to use. I mean, how often is a polynomial annoying? We're thankful whenever we see polynomials most of the time in a math class, right? Polynomials are easier. And I mean, that's an oversimplification, but we'll worry about that down the road in another class. it is possible to represent this function as in an infinite polynomial, as long as you are in this window. And that is actually super useful. This brings us into the topic of representing representing functions as power series. Now, where did I hide those notes? Oh, there we go. Representing functions as power series. It's a big thing. It's a big deal. And we are going to look at that now. So one, we can know power series will always work. And two, it turns out that ever so often, a power series can represent some function that we might care about. Now, at this point, the only function we know how to represent with a power series is the one that I just described to you by the geometric series. We know that the series from n goes from 0 to infinity of x to the n is actually 1 over 1 minus x. I can think of that as the function 1 over 1 minus x, and it converges absolutely to that function 1 over 1 minus x, which means in any equation where I have 1 over 1 minus x as a part of that equation, I can, at will, substitute the series x to the n goes from 0 to infinity, and no one's going to know the difference. It'll look different, but it won't actually be different. It's just like someone substituting a half or 0.5 somewhere. Well, yeah, it looked different, but is it really different? No, not really. You just wrote that thing in another way, right? Now, hopefully by the end of this class, I'm going to show you some of the possibilities that can happen from that. But for now, let's actually run with this a little bit. Let's actually see how we can use known power series to figure out power series for functions that we don't know their power series, okay? And then I'm going to actually show you, I don't think that's going to be today though. I'm going to show you a way where we can generate power series of functions from scratch. So even if I don't know the power series for a familiar function, I can actually figure out a way to find a power series for that function. But let me show you how to use a known power series to find the power series of some other function. For example, find the power series representation for the following functions. Indicate the intervals where the power series are valid. So here's an example. Let me run through it for you. I have the function 1 over 3 plus x. Now, for whatever reason, this is not a representation that's useful to me. I would much rather be able to think about this function as a polynomial. Let's say for whatever reason that's coming up, right? How can I actually do that? How can I get to represent this as an infinite polynomial or as a power series? Well, I know a power series already, 1 over 1 minus x. And then I look at this and I'm like, well, you know, algebraically speaking, it's not the same as 1 over 1 minus x, but it's actually close enough. Like if I start to maneuver things a little bit, algebraically move things around, what I can do is I can factor off a third, and that's going to look like 1 over 1 plus x over 3. Which now it looks like 1 over 1 plus something. Now, of course, I want 1 over 1 minus something. So what I can do is I can just write that plus as a negative of a negative, right? So algebraically, this is the same as me saying this. Now this, I can just think of this as the sum of a geometric series. Think of it as 1 over 1 minus r, where the r is minus x over 3. Another way I can do it, think about it, is just think about what 1 over, if I look at this and plug in on the right side minus x over 3 in place of x, then it's the same as plugging in minus x over 3 in place of x on the left side. So that's a couple ways you can see this. So this here is just going to be the series of minus x over 3 to the n goes from 0 to infinity. So either see this as the sum of geometric series, or plug minus x over 3 for x in the equation x to the n equals 1 over 1 minus x. So if I plug in minus x over 3 into both sides of that equation, the right side is going to look like this that I have over, the right side is going to look like this that I have over here. And the left side is going to look like this series. So now I can actually clean this up a little bit. This is going to be minus 1 to the n, x to the n, over 3 to the n, and then I bring in the third back, and that's 3n plus 1. And now I have represented the function 1 over 3 plus x as a series, as a power series, in fact. Now, where does this work? Well, again, I know that this one, the series that I'm modeling this off of, it works when my x is between 1 and minus 1. So here, this is going to work if my x over 3 is between minus 1 and 1 by comparing to that. So this means this guy is going to work for x between minus 3 and 3. The longer way is to actually do the ratio test, but we don't need it here because we already have the interval from the original. So it definitely works there. And so the interval of convergence for this guy is going to be minus 3 to 3, which I figured out from here. Okay, so just take some time to absorb what I just did. Here was a function, this seemingly random, inconspicuous function. I want a way to write it as a series. Now, I already know how to write some familiar function as a series, so all I do is I algebraically manipulate this guy to look like that guy that I already know how to find a series of, and then plug it into the formula for that series. I automatically get another power series representing that function after some simplification, and the interval of convergence of the previous series informs the interval of convergence of this new series that I just created. So I can think of this function, 1 over 3 plus x, I can think of it as this series as long as my x is between minus 3 and 3. Okay. Now, hopefully we kind of see how that works. Let's worry about this one. All right, ideas on how to do what I just did for this one. Any ideas? It's exponential. No, it's not exponential. Is it alternating? No. Oh, sorry. Oh gosh, you guys crack me up. Now, I can tell you what a few of you are probably thinking, or I don't know. Some of you are just like, I don't know what's going on. Okay, so you might be able to think of it as this and that. And then you can say, well, I know how to express this as a series, and I know how to express that as a series. However, that would require you to multiply out. Which is very annoying with a capital very and a multiple underline. Very annoying. Especially if you wanted to regroup and P series. It's not a P series. Okay. So, all right. Yeah. All right. So here, so I wouldn't want to do this. That's probably what a lot of people were thinking in the beginning, but it's not the way to go for this, really. There's a nicer way to get through this. Here's a hint. Think calculus. All right, now, take the fact that you know how to do this guy, and then look at this guy, and come up with a way to connect those two via calculus. What would you come up with? If I had to connect this guy to the guy that I found before with calculus, what would be a way to connect those two? It's the derivative of the previous one, right? Well, not exactly, right? It's off by a sign. Note, if I take the derivative of 1 over 3 plus x, I would get minus 1 over 3 plus x squared. In other words, 1 over 3 plus x squared is actually the negative derivative of 1 over 3 plus x. And here's the thing. I know how to express this as a series. Hey, I know a series for that guy. And now you're like, well, can I differentiate the series though? So I would actually plug that in. Remember, the series can just replace the function. I would plug in the answer that we got before. And that would be minus 1 to the n x to the n over 3n plus 1. And Natalie's asking the right question. Is it legal? How am I going to differentiate this? In fact, I can move this inside, and I can differentiate each term of the series with respect to x. I can, in fact, that's just a power rule, right? Add 1 to the power divided by the new power. So the integral of that is the derivative divide. I'm doing integral. The derivative is just going to be n x to the n minus 1. Of course, this part here stays. I would have a 3n plus 1, and that's the derivative. And then I have the series of that. There's a minus sign on the outside, but I could bring the minus sign on the inside, and it would look like n goes from 0 to infinity of minus 1 to the n plus 1. Nx to the n minus 1 over 3 to the n plus 1. Now, notice that this doesn't quite look like a power series with the n minus 1. Well, I'm going to clean up later, but maybe before that, I should actually move on. So let's make sure we can answer Natalie's question, because it is actually a valid question. This switch that I make right here, this little switcheroo where I decided, you know what, I'm just going to differentiate the terms of the series. Why is that legal? Let's use paying attention. Why is that legal? Why am I allowed to do that? Why am I allowed to switch the series notation and the derivative notation and just differentiate the series part? No, it's not constant. This is actually a function, right? If it were a constant, the derivative would just be 0. No, not because of the polynomial. Polynomials are, by definition, finite beings. Here I have an infinite series. Why am I allowed to differentiate each term and think that that makes sense? Okay, so if we think back, there was a point in time where I said something like, oh, you know, there's this theorem and it basically means that if I rearrange the terms, then I can get a different answer, but, you know, I don't want that to happen. So I want a kind of series that it doesn't matter if I rearrange the terms. That way I can like distribute stuff across the series and I can do all this math with the series and I won't have to worry about the answer being defined or legal. And there was a reason for that. So that was called the rearrangement theorem. And what does that mean? Why was I allowed to do this in this case? You guys remember that? It has to do with the convergence of the series. And the fact that it converges absolutely. Whenever a series converges absolutely, I'm allowed to do this. I can actually do calculus on the series. If the series was conditionally convergent, I cannot do this. Because then if I distribute my derivatives across the series, then someone rearranges it, suddenly my derivative changes. My derivative would be effectively undefined, right? If someone can change the order of terms and then my derivative distributes across it and then the answer can change, then you can't really say you can find a derivative. It's not going to make any sense. This is allowed, I can switch the derivative and the series symbol because the series converges absolutely. One, it's a power series, so I know wherever it converges absolutely. But we also proved this by the ratio test, which gives absolute convergence automatically. So this is allowed because the series is actually absolutely convergent. Now, notice here that just to clean this up a little bit, n equals 0 gives a zero term. So we can start at n equals 1 if you wanted to. Which brings us to me writing the series in this way. Now at this point, we already have the series. This is just a little bit of cleanup. I want it to look more like a power series for you guys. It is a power series, but I want you to be able to recognize it as a power series. Now, of course, if my n equals 1, then I have the power 0, then I can keep going. And so what I can do here is do something that's called shifting the series. This is also something that you'd have seen in Calc 1, I think. So you can set shift all n's to n plus 1s. And so here, everywhere I see an n, and I'll write out the step this time. Everywhere I see an n, I can write instead an n plus 1. This is going to be fun, filling in all the gaps. Okay, so that's going to look like minus 1 to the n plus 1 plus 1. This is equal to 1. This is equal to n. This is x to the n plus 1 minus 1 over, now this is 3 to the n plus 1 plus 1. All right, so I can make a shift. Everywhere I see an n, write it with an n plus 1. And then finally, the last bit of cleanup. This actually looks like 0. Taking a lot of space for this. I should have finished the 3 examples in this time. This is equal to x to the n over 3 to the n plus 2. And so I can say that this function is that series. It's called an index shift.
Professor?
Yes.
Why do you have to add the n plus 1? Like, why do you have to do that?
It's cosmetic. I want it to look like a power n.
The power n? What happens if you don't do that?
Then you may or may not recognize it as a power series. The definition of our power series has the n as the power. So I literally just shift my n's to get it to look like that definition.
Do you think students will still get the correct answer if they don't add the n plus 1 in this case?
Well, I'll say this. If I'm doing a multiple choice problem, I would not put one of the answer choices with an n minus 1 power. So you would have to figure out how to get from one situation to the other. This is going to be something cool. I don't know if it's going to run into the other one. Yeah. I don't know. Give me a sec. Just want to move some stuff around. But what's coming up, I don't want to actually spoil the surprise. Some cool things are on the horizon. I don't want to spoil the surprise. Okay, and we're back. Okay, so here's the last one. Now, taking my cues from what the last example would look like, let's actually figure out a power series for this one. Now, of course, here I'd recognize this. Note, ln of 3 plus x is actually the integral of 1 over 3 plus x, right? When x plus 3 is positive, which we can assume that. So now I can actually plug in the series that I know for that. And we found that earlier. Minus 1 to the n, x to the n, 3n plus 1. So I plug that in. Now what I'm going to do, because of absolute convergence, I can switch these. I can, instead of looking at the integral of the series, look at the series of the integral. That amounts to doing the power rule on this integral here. So this is going to be look like x to the n plus 1 divided by n plus 1. Now, of course, there's going to be a plus c. So that's this guy. Now, to find the plus c, let's plug in a nice value. What's nice? Say x equals 0 would be nice, because then I won't have to worry about the series part. If I plug in 0 in the series, all the terms go to 0, and I would just have c on that side. So then I would get ln of 3 plus 0 is equal to c. So this means, ultimately, my ln of 3 plus x is equal to the series of this minus 1 to the n, x to the n plus 1 over n plus 1 times 3 to the n plus 1 plus ln of 3 separately. Now, I can do my index shift to make that look more like a series if I wanted. So let's do something like shift all n's to n minus 1s. That'll give me x to the n on top. It would only give me n down here, and it would give me 3 to the n right here, plus ln of 3. So now that looks like a power series. Where this guy here just represents your C0 term. And then from 1 to infinity, I get all the others. Now, I just want you to realize, note that we're allowed to integrate and differentiate each term because of absolute convergence. I mentioned that earlier, and I just want to put that together here. Right? So because to differentiate and integrate series and terms because they absolutely converge on the interval where we're considering. Okay, and this is called, by the way, term-by-term integration and term-by-term differentiation. That's the name we give it when we switch an integral sign and a series sign, or we switch a derivative sign and a series sign. It's called term-by-term. So you can essentially move calculus towards the inner terms. And that's called term-by-term integration. Here's something cool about the last example, right? So this is something I mentioned before, but I actually want you guys to see it in person. What if I plug in x equals 3 into this example? And yeah, originally 3 was not within our domain of convergence, our interval of convergence. However, with this now being alternating and the n at the bottom, you can actually check using an alternating series test that this actually will converge at 3. So the convergence is conditional, but let's actually use that to our advantage. So if I plug in x equals 3, on the left side, I would have ln of 6. On the right side, I would have minus 1 to the n minus 1 over n, because the 3's would cancel, right? The x to the n becomes 3 to the n, and it cancels with the 3 to the n in the denominator, plus ln of 3. What I can do now is I can move the ln of 3 to the other side. This gives me ln of 6 divided by 3, which is ln of 2. Now, I am going to multiply both sides by minus 1. And why would I do that? Is because I want you to see something that's familiar here. If I multiply this side by minus 1, I would get minus 1 to the n. And look at that. Now remember at some point, I don't know, 2 or 3 classes ago, I mentioned to you that this is the alternating harmonic. And I told you that that guy converged to minus ln of 2. And you might have wondered, well, how would you know that? How would you figure out that something like that, which looks like a bunch of fractions, a bunch of rational things, right? This is equal to minus 1 plus a half, minus a third, plus a fourth, minus a fifth, plus a sixth. How would you figure out that that actually adds up to ln of something? Where did that ln even come from? Well, now you see where it comes from. It actually came from us figuring out how to sum an infinite series by actually looking at it as a power series that represents a function. And because I can just plug things into functions, or I can plug things into polynomials, it makes it easy for me to figure out what a series is. So there are a bunch of series that we use tricks like this to actually figure out what they add up to. So when I tell you, oh, the series of 1 over n squared is equal to pi squared over 6, and you're like, how did you get that? Well, we're not going to learn in this class how you get that, because you actually need multivariable calculus to figure that one out. At least one of the easiest ways I can think about is to use multivariable calculus. But now I just use calculus to compute what this series is by figuring out how to compute some function as a power series. And that's pretty cool. At least I think so. And believe it or not, it wasn't the coolest thing I wanted to show you guys today, but we're kind of out of time. Time flies when you're having fun, or when you're guessing things that are exponential, or is it alternating? Is it exponential? It's amazing. I've never seen so many wrong guesses in such a short time. Hopefully you guys can get better by Saturday. It is actually pretty cool. I agree with you. Believe it or not, it's not the coolest thing I have in store for you guys. I was hoping to get to the other thing today, but I guess we'll have to move it and do that tomorrow. But yeah, here we just figured out the alternating harmonic is equal to minus ln2. Very serendipitous. Not what we were expecting to get out of it, but now we start to see. Hopefully this is also giving you some idea of why knowing about power series is useful, because now we're able to add up an infinite number of things in a very efficient way. And we're going to see more uses of power series pretty soon. But leave that as the first intro. This is introduction to power series. This is what a power series is. We know how to determine where they converge. And we also now know how to figure out power series representations of functions when we know power series representations of similar functions. That's what we covered today. I wanted to cover another application today, but we'll move that in for tomorrow. I think it's going to be cooler than this application. I think, but we'll stop there for now. Yeah, kind of bummed that I didn't get to the other one. You know, I snapshotted pictures and everything for it. Yeah, but. So, yeah, so we get, I know something that might make me feel a little bit better. So we get that the alternating harmonic and let me find that guy. Where was it? Okay, there we go. Okay, I'm gonna feel a little bit better. I got to put in some picture. Okay, so that's how we figured out that was ln2. Wow, okay, awesome. All right, I now know how to add up an infinite number of things. That seems crazy that it would add up to an irrational number because I'm adding up an infinite number of rational things. But hey, this alternating harmonic series can represent a log function at a very specific point because this series represents a log function. And that's how I know. All right, we're going to stop there. Kind of bummed we didn't fully get to cover what I wanted to cover, but it's fine. We are going to wrap up. We will start on that tomorrow. That being said, some of you do need to review what we did here. Some of you are still kind of iffy on series. Some of you are not able to tell when a series would converge versus diverge. That is something that you need to have like under control. You need to be able to look at a series, and for most series, like all the series that I put up in today's class, these are series that you guys should actually spotted whether or not they converge within a few seconds. It shouldn't take you a long time. So if you guessed wrong, or it's something that you need to wrap up for the test. That being said,
Professor,
yeah.
Is approximating errors it's going to be on Saturday's exam? Approximating errors.
Yes, as in the alternating series approximation theorem, yes. Approximating errors for Simpson's rule and trapezoid rule, no. But approximating the error for an alternating series,
like yesterday,
yes.
like, you know, the accuracy.
Yes.
But the thing is that we're not going to use a calculator.
I know, you don't need a calculator. Anyway, that being said, hope you guys enjoyed it. Tomorrow we'll look at some even more cool stuff. Good night, everyone. Stay safe, and I'll see you in the next one. Ciao.